Okay. Give a minute for people to come in. So let's get started. Okay, so we're gonna go over factorizing and division algorithm for polynomials, and then I'll go over like an interesting example. I think your professor started it. It was on like Gaussian integers, z adjoin I, but okay. Factoring polynomials over f of x, right? So, let's say f is a subfield of E, right? So why do we want to factor? It's because if we basically, if I give you a polynomial, right, the interesting thing is finding zeros of it, right? So we say alpha in E is a zero if basically f of alpha is a zero of f of x. If if you plug it in, you get zero, right? And this is zero in E, right? So, right. So in general, right, these two things are fields. So in general, right, if we could factor, then it's easier to find roots, right? Because then we have that f of alpha is g of alpha, h of alpha. This is multiplied, by the way, right? So if f of alpha is zero, what does that tell you about these two guys? Or these two things? If f of alpha is zero. So where does g of alpha and h of alpha belong? So they belong to a field, right? And in a field is in particular an integral domain, right? So if a product of two elements in an integral domain is zero, one of them has to be zero, right? As is integral domain. Right? So we sort of reduce the problems to like factors. So we basically want a way to factor polynomials, and another way to say that is dividing, right? So we have a division algorithm. Over f of x, or let me just say for f of x. Let f of x, g of x be in f of x. So from here, right, obviously, I mean, it doesn't have to be like, let's say degree of g is bigger than zero, right? Because, I mean, we all know how to divide if degree of g is equal to zero, right? It's pretty obvious, right? Because, like, f of x is like an plus a naught, right? And g of x is just some number c, then obviously this is just Yeah, if you just, it's like you're just multiplying by a number, right? Oh, sorry. Yeah, you're multiplying by like 1 over c, right? So, and of course, since E was a field, right? In a field, you can obviously like divide, right? Everything has an inverse. Of course, G is not 0. But so obviously, this kind of like the trivial case, so we sort of assume degree of G is bigger than 0. Then what? So then there exists unique. So does everyone know this notation? So when I put exclamation mark, it means like unique. Yeah, it's just a shorthand for writing unique. Unique polynomials g of x and r of x such that f of x is, no, sorry, I want to say q of x. G of x times q of x plus r of x. And obviously there's some condition on r, right? Obviously you could divide many ways, right? So what's the condition on remainder? So if I forget this problem for now, let's work in z. If I told you 3 divided by 7, right? What is the remainder? Like, what's the condition on the remainder? Like, can I do this? 1, and then say 4 is the remainder? Yeah. So in general, what do you think is like the thing, like here, right? Obviously this must be 1, right? So in other words, like the remainder in a sense has to be smaller in size to what you divide by, right? Everyone agree with that? I'll put size in quotations because that's kind of an ambiguous word right now. So obviously your remainder has to be smaller than 3, right, in a sense. So it over z, what's the function that sort of measures size? Like, does anyone know? I'm 100% sure you know this. There's no such thing as degree in z. Z is just numbers. So like, what's degree of, like, over z, there's like no such thing as degree. So I'm saying you all know this. So like, how can I tell a number is like, kind of bigger in size? Forget negatives, right? Like positive numbers, like uh absolute value. Good. Yeah. So basically remainder must be smaller in absolute value, right? Remainder must be smaller in absolute value to what you divide by, right? So in z, the size function, some people call it like norm, right? Hopefully that rings a bell to what you learned in Gaussian integers. There's a norm. So the norm function is sort of like absolute value, right? So basically, the same thing here, right? So here, r of x must be smaller in size to g of x, right? And someone said it, right? What is the size function for like polynomials? Someone said in the chat already. So how do you measure like how big a function is? How big a polynomial is? Take that back. So it's degree, right? So in this case, size is degree. Yeah. So your r of x must be smaller in degree to whatever you divide. So it's always like whatever your size function is. Oh, sorry. so r of x, sorry, it's 0 or degree r of x less than. I don't know why. I think the book, when they say degree 0, they mean like non-zero terms. I guess they sort of regard 0 as something else. But okay. Is everyone clear on this? At least division algorithm is, just think of dividing in z. It's like an analog of dividing over integers. So everyone follow? Okay. So from here, let's continue. Let's do an example. Let's say in z5 of x, right? I'm just gonna go over this pretty quick because I'm sure you all know how to long divide. So obviously, basically in z5, you can change anything, but I don't know. Let's just keep the 7 for now. Yeah. So you do x cubed, right? So you get x to the 5th plus x cubed, right? If you subtract, you're gonna get what is it? Negative x cubed plus 3x squared plus 7x minus 1, right? So now we have to get rid of the x cubed. So what is that? So I think it's minus x, right? So negative x cubed minus x. Subtract. So I get 3x squared plus 8x minus 1. So here's the benefit of being in z5. You could have changed to 7, but here, right? What is 8 in z5? In z mod 5z? What is 8? You can obviously work with 8, but I mean, so I'm just showing for example. You could choose anything, right? You could change this to 3, right? So I'm saying like in Z5, you can always change your constants to up to equivalence classes. So I mean, if you really want to be a masochist, you can do like instead of 8, like this is Z5, you could just add multiples of 10, right? You could use like 8, you could use 800. Sorry, no, not 800, not 800, 808. 8,000,008. You could use whatever you want. So, and then from here, right, it's plus 3. So, and then you're done. So negative, what is that, 3x. So negative 1 minus 3 is negative 4, right? This is the negative 4 is the same as plus 1, right? Yeah. So this is your remainder. So this is like your, if you like, this is like your g of x. This is like your f of x. This is your q of x, and this is your r of x, right? In the description here, right? So again, so basically f of x is, so what I mean is you could have changed the 7 here to a 2. I don't know, up to you. So x squared plus 1 times x cubed minus x plus 3 plus 3x plus 1. Yeah. Okay, everyone follow with this? And obviously, degree of remainder is 1, right? This is degree 2. So it certainly satisfies the division algorithm. This thing's degree 1. Is everyone clear on this? This is like algebra, except your coefficients are in like an arbitrary, just not, instead of z, it's z mod 5z, right? So I trust you can all do this. So there's another example, you might think like it's just integers and polynomial rings, right? Because that's what you learn in algebra. You know how to divide numbers, and you know how to divide like polynomials. So there is another interesting ring where there is a division algorithm. I mean, in fact, there's a lot, but the interesting ring is called the Gaussian integers. I emailed the professor about something because I feel one of his definitions is a bit off, but I'll talk about it later. It's like a word of caution. I mean, his definition is correct, but it's only for this ring. So, or a certain class of rings. So, Gaussian integers, some people call it Z adjoint I, right? That's how people like, you know. Uh, but if you like numbers, some people also write in what is I? I is root -1, right? So of course, it's exactly what you think, right? It's basically complex numbers such that A, B is in Z, right? As a set, right? So um, it's a complex number, right? So what is what is the norm in this case? Like, how do you measure the size of a complex number? I mean, similar to what you do in Z, right? So how do you measure like the size of a complex number? Yeah, I mean, it's just multiplied by conjugate, right? But or sort of, right? So it's just multiplied by like a minus bi. Yeah. You. I mean, this is if you like. Yeah. So this sort of like our norm function, right? So later on, this will be like what we mean by remainder. When we divide, the remainder has to be smaller in size. We just like normalizing it. So if you like, uh, yeah, I guess it is that. But I mean, how about this? If you don't like this, it's the square of this. Yeah, it's like the square of the thing. It's because we don't like square roots. So we sort of just take the square norm. Yeah. And basically what we because we sort of wanted to satisfy something like the kind of like absolute value. So if I tell you in Z, right, you have something like this, right? This is the same. This is just this, right? Does everyone agree? Like absolute value of x times y is just absolute value of x times absolute value of y. So some people write this as norm of a plus bi, right? It's a squared plus b squared, right? Uh, or if you like, it's norm of x for x and z mod I. Yeah. So here, right? So we sort of want this. Basically, you could check this. This property also holds. It's multiplicative. Yeah. So when you take the norm of x times y, it's the norm of x times the norm of y. Yeah. So it's multiplicative. So what I mean is you could what I mean by check is if x was a plus bi and y was c plus di, here you would do the multiplication first and then take the squares, as opposed to here it's a squared plus, I mean, if you like, just check this, right? A plus bi norm of c plus di. I mean, this thing is a squared plus b squared, right? Times c squared plus d squared, right? So you could check that it's multiplicative. So why do we like this? Well, let's figure out like what are the units here. This should be quite simple, right? If does everyone agree that the norm of a plus bi, where ab is in z, right? An element of my Gaussian integer. Does everyone agree that this has to be an integer? I mean, if a is an integer, b is an integer, a squared plus b squared is an integer, correct? So automatically, you sort of see what the units are, right? Because suppose x is in z is a Gaussian integer, and norm of x is like, obviously it's positive, right? So let's say it's bigger than 1, right? If you like pick a number like 2. If x was a unit, right, then x times x inverse is 1, right? Again, remember, what does unit mean? Unit means there's a multiplicative inverse, right? But if this is true, then it must be true for the norms. What's the norm of 1, everyone? Right? So, side note, norm of 1 is just norm of 1 plus 0i, right? And I know norm of a plus bi is a squared plus b squared. So this is 1 squared plus 0 squared, which is 1. Yeah? So this is 1. On the other hand, by the property here, right, I know that this is just norm of x inverse, right? So what does that tell you about norm of x inverse? Right? It tells, I know that norm of x inverse is 1 over norm of x, but if norm of x is bigger than 1, is 1 over norm of x an integer? Like, is this in z, is my question. Anyone? It's not hard. It can't, right? It can't be in z, right? Because norm of x is bigger than 1. I mean, it's an integer that's bigger than 1. So I mean, the smallest it could be is 2. So it's like a half, a third, a fourth. So you see, if your norm is bigger than 1, there is no inverse, because the inverse would have to have fractional norm, right? And we agreed that the norm must be in z, right? And so that's one way, right? And then the other way is, well, if I am norm 1, so obviously if I'm going to be a unit, I have to be norm 1, right? But then you ask, like, are all things norm 1 units? Well, you could just check that, right? If norm of x is 1 and x is a plus bi, then that means a squared plus b squared is 1, right? Where ab is in z. You're going to realize there's 4 solutions, right? 1, 0, 0, 1, negative 1, 0, 0, negative 1. Everyone agree? I mean, AB must be integers. So, of course, if you're allowed fractions, then, real numbers, there's infinitely many solutions. But A and B must be integers. So you see that these are the only solutions, right? So you just check it by hand at this point. 1, 0 is what? It's when A is 1, B is 0. So that's just the number 1, right? 1 plus 0i. Here it's I, right? 0 plus 1i. Negative 1 and what is this? Negative I. And all of them have units, right? The inverse of this is itself. The inverse of negative 1 is negative 1. The inverse of I is what? I squared is negative 1. So the inverse of I is negative I. And the inverse of negative I is just I, right? So indeed, like you see that x in, so let me just go to the new tab. So x in z mod I is a unit if and only if x has norm 1. Everyone agree so far? Follow? Does everyone follow? Like, I know it's like a new ring, but seeing the connection between. Okay, so the question was, what are units in here, right? So I'm saying let x be in. So my claim is the units of z mod I are those with norm 1. That's the answer. So what I did before was okay. So the first step. What would the first step be? Check those with norm bigger than 1. Are not units, right? Everyone, do you follow? So first step would be, and that's what I did here, right? Did I? Oh yeah, I must have erased it. So I assumed that, right? Norm of x was bigger than 1, and then I say, okay, let's assume it's then let's suppose by contradiction it is a unit. So there's an inverse. Then norm of x times x inverse is norm of 1, which is 1. This is, I told you, it's multiplicative, right? So norm of x inverse. So the inverse must have norm 1 over norm of x. But if norm of x is bigger than 1, this thing is not in Z. Yeah? So I know it can't be a Gaussian integer. So I know x inverse cannot be a Gaussian integer because we said right here, right? Right here. The norm of a Gaussian integer is an element of Z, right? And here it's not. So I know x inverse cannot be a Gaussian integer. So anything with norm bigger than 1 is not a unit. So that's the first step. And then obviously, what's the last step? Well, second step, check all elements of norm 1 are units, right? So once I check everything bigger than norm 1 is not a unit, I still need to check that everything that is norm 1 is a unit. And that's what I did here, right? If I'm norm 1, right, let x be a plus bi, then the norm of x is a squared plus b squared. And I know that's 1. So I have, like, if you think about it, there's only 4 choices for a and b, right? Because a and b must be integers. So it's 1, 0, 0, 1, negative 1, 0, 0, negative 1. Okay, great. So from here, right, we get to find what prime is. So here's the thing that bugs me. The professor he gave the definition of, like, irreducible, which isn't, in this case, it is the definition of prime. But yeah, so let me just say this. Caution, definition, you'll see why. So if something is irreducible if it cannot be written as product of 2 non-units. Right? So in other words, it's irreducible if the factors are like itself and a unit. Right? It's kind of like in the integers, right? Something is, if you think of later on, in this case, this is equivalent to being prime. So a prime number, right? The only factors are like p, like, and like 1 and like negative 1, right? I guess negative p2, but like, like it's only p and then like some product with units, right? So in this case, the units of z, right? If you think of what the units of z are, what are the invertible elements of z? Well, it's 1 and negative 1, right? Because any other integer, like 2, the inverse is a half, which is not an integer, right? So this does sound like the definition of prime, but it's actually not. So I actually emailed the professor saying what like is this what he wanted. So the actual definition of prime is if if p divides ab, then p divides a or p divides b. Does everyone see the second definition, right? So like if I had a prime in z, like call it 3, if it divided 6 and 5, then 3 must divide 6 or 3 must divide 5, right? Does everyone agree with that? I mean, at least do you agree with this definition on the level of like integers? Like if I give you something, if I tell you like a prime divides something, it must a product, then it must divide one of each, right? Yes? No? Does everyone follow? Right. So here's the thing. In this case, over zi, these two definitions are equivalent, are same. So you're fine to use either, right? But let me just give you a quick counterexample as to why these two are different. If I consider instead of this ring, so root negative 5, right? So similarly, you can show like, norm of a plus root negative 5b. This is instead of a squared plus b squared, it's a squared plus 5b squared, right? And similarly, you can show this. The units are those of norm 1. Same proof of norm 1. So from here, right, this element is the number 3 is irreducible. Why is that? Because I can't write it as a product of two non-units, right? Because let's suppose I can write it like this, where x and y both non-units, right? So we're gonna do a contradiction proof. So then norm of 3 is norm of x, norm of y. What's norm of 3 here? It's so 3 is 3 plus 0 root negative 5, right? So this is 3 squared plus 0 squared, so it's 9. So what are all the factors of 9? What can I have? I know it must be positive, so I could either have 3, 3, 9, 1, or 1, 9. Does everyone agree with this? I mean, it's just, well, it can't be this one, it can't be this one, because we assume that they're non-units, right? So it must be 3, 3. But if you think about it, what thing, if a squared plus 5b squared is 3, right? You see that this thing must be 0, right? Because b is an integer. So once b is any non-zero integer, this thing's already bigger than 5, right? So you see b must be 0. So a squared must be 3, but this forces a to be plus minus root 3, which is not in z, right? So you see it's sort of impossible to have norm 3 here. So you see 3 is actually, this is not possible. So 3 is irreducible. So I cannot write it as a product of two non-units. But here's the thing. 3 divides 2 plus root negative 5 times 2 minus root negative 5, right? Because this is 2 squared plus 5 times 1 squared, which is 9, right? I mean, just do the foiling if you don't believe me. Right? 3 divides 9, right? So, but 3 does not divide 2 plus root negative 5. 3 does not divide 2 minus root negative 5. Right? So you see here, right? This definition is not satisfied. Right? I divide a product, but I don't divide either of the individual terms. But it's still irreducible. So that's sort of why I emailed the professor, like saying, because I think he gave you this definition, right? A prime is if the only factors are itself and a unit. Well, if norm is 3 times 3, so if norm of x is 3, let's let x be a plus b root negative 5, right? I mean, the x is just an element in this ring. So norm of x is 3, but it's also, from here, it's a squared plus 5b squared, right? So I have a squared plus 5b squared is 3. What must the solutions be? These are two positive things, so yeah. So you see b must be 0, and then, yeah, so you see it's not possible to have norm 3. So that's sort of why I emailed the professor already. I don't know what he wants, but so let me tell you, you don't have to worry about this, because this ring, the reason it holds in, let me just erase all this. So the reason being is that in the Gaussian integers, factorization is unique. So the key point is in here, the thing you're doing, factorization is unique, right? Factorization is unique. So what I mean is, obviously some primes, don't become primes, right? Like 2, I think he gave that example in class. But this is the only way to factor 2. Like, it's unique. But like here, right? For example, 6 is 2 times 3, but it's also this. Yeah? So this ring is really bad, because there's no unique way to factorize. Like integers, right? If I tell you, like, integers factors as 6 factors as 3 times 2, you're not going to question me saying, what if there's another possible factorization, right? Here is not the case. 6 is 3 times 2, but it's also this, right? So that's sort of the issue here. So since he only went over Gaussian integers, you're pretty, it's okay to use this definition, is what I'm saying. Yeah. But I'm saying be careful, because other books will certainly define prime as this. And I just want you all to understand why they do that. I think people, like all other books, define primes this way. So there's like a key subtlety here. Okay, with that being said, can we continue? Does everyone follow? So over z adjoint I, like you can use either definition. Okay, so z adjoint I is a nice ring. So division algorithm. So I think this is why he went over this, because z adjoint I, there's a way to divide here. So what do I mean by this? Well, let's divide. What is 4 plus I divided by 2 plus I? So, I mean, obviously this is an element of z of I. This is an element of z of I, right? So you know how to divide complex numbers. So how do I make this in terms of like something plus something I? How do I make the denominator a number, like without like i's in it, like just like some real number? Conjugate, good. So what is this? This is what, 5? I think this is 5. And this is just algebra. You just FOIL. I'm bad at foiling, so please tell me if I make a mistake. So this is what? 9 minus 2i over 5, right? So obviously this element is not here, right? Not in here. Because these are not integers, right? So that's where the remainder kicks in. So let me just draw a grid. You'll see. If this is the complex plane, right? So this is I, and this is like the real numbers, right? So this is Ri, and this is the real numbers. How would you graph the Gaussian integers? So on the graph, right? How does it look like on a graph? It's all integer points, right? So you sort of see it's like a grid. So you have 1, 1, 1, 2, this one. Like it's like it's just, the Gaussian integers are just like it's like a whole grid, right? Do you all see this? Because you only want integers like a plus bi, where a and b are integers, right? So it's like a grid, and then same thing for bottom. Okay, I'm just gonna go up to here. Does everyone see this? Right? Like it can't be anything like inside the grid, right? Because you're only allowed a and b are only allowed to be integers, right? So for example, like this point, it's 4 plus 1i. Yeah. Does everyone follow here? So that's the point here, right? Whoa, what happened? So that is the point. 4 plus I is this point, right? 2 plus I is right here, right? So after you divide, where is 9 over 5 minus 2 over 5i? So 9 over 5 is like 1.8, right? So it's like something here, right? And then negative 2 over 5. So like somewhere here, right? Does everyone agree? Our point here, this is 9 over 5 minus 2 over 5i. Approximately. Does everyone follow with this? Yes? No? Okay. Well, you're done. You're done dividing because your q of x is whatever's closest to it. So out of the four corners, so out of these four corners, right? Because it's sort of closed in this box. Which one is it? Which corner is it closest to? Let me yeah, 2, 0, right? So you see when you so it's actually just this. So 4 plus I is 2 plus I times 2. 2, 0 is just 2, right? And then plus r of x, right? Whatever remains. So in this case, what is r of x? R of x is, so this is what, 4 plus 2i. So r of x is 4 plus I minus 4 minus 2. It's negative I, right? So not r of x, it's r. It's not a polynomial, so it's like negative I. So this is your remainder, right? This is sort of like your q. This is like, I don't want to put like x, right? Because it's not a function. But so question, what's the norm here? That's why your professor calls it norm, right? So how do you check the norm is smaller? Well, I need to make sure the norm of negative I is smaller than norm of 2 plus I. But norm of 2 plus I is, again, a squared plus b squared, right? So 2 squared plus 1 squared, which is 5. Norm of negative I is obviously 1. Or if you like, negative 1 squared, which is 1. So obviously this checks out, right? So you can actually divide in the Gaussian integers. Yeah, so when you divide, you might not get something in z. So you just pick the corner it's closest to, and then that's your q, and then your remainder is whatever remains. so this is like division algorithm in the Gaussian integers. Just solve for it, right? mean, this is R. Just so this is 4 plus 2i, this is 4 plus I. So what do you need to add to 4 plus 2i to get 4 plus I? It's a it's a negative I, right? So yeah. So the choosing closest to corner, think of that as a way to make remainder have smallest norm, right? So okay. So let's do it. I heard he's going to give examples on Gaussian integers. So I think this might be one thing he might give on. I mean, I don't know if the homework's posted yet, but here's an interesting thing. So if you recall, two is not a prime here, right? Because 2 is 1 plus I, 1 minus I. Agree? So 2 is not a prime in this case. So basically, let me tell you something. Let's let P be congruent to 3 mod 4 in Z. Yeah? P prime. So P is the primes that are like 7, 11, not 15, 19, so on and so forth, right? So the question is prove P is prime in Z adjoint I. Yeah. So again, being prime in Z, you need not be prime in your Gaussian ring, right? As we see here. So here I'm saying primes congruent to 3 mod 4R. So let's check this, right? So assume by contradiction, P is, say, X times Y, right? I mean, if you like X is A plus BI. I just don't want to write I just don't want to write this all the time. So I just put X times Y. So P is an honest integer. So let's take the norm. Obviously, norm of X is, norm of product is product of norm. What is norm of P? So these are non-units. What is norm of a prime? Come on, you all know this. Like what's the norm of 7? What is the norm of 7? No, like is it like what is norm of 7? It's this. Yeah, 49, right? So this is P squared, yeah. Yes, I think most of my questions are not trick questions, so don't be afraid to answer. Okay, so this thing is what? This thing is A squared plus B squared, and this thing is C squared plus D squared, right? So you have two choices, right? You have PP, right? P squared 1 P squared, right? Same exact argument as last time. But these are non-units because we're assuming by contradiction it's not prime. So it can't be this, it can't be this, right? Because units, as I said in the beginning, are norm 1. So it must be this. Now P is equal to, P is equal to A squared plus B squared. Is this possible if P is 3 mod 4? So let's consider it. So all the squares mod 4, 0 squared is 0, 1 squared is 1, 2 squared is 0, 3 squared is 1, right? So all the squares mod 4 are either 0 or 1, right? So I could have this as 1, 1, 0, 1, 1, 0, or 0, 0, yeah? So 1 plus 1, 0 plus 1, 1 plus 0. So when I take everything mod 4, right? or 0, 0 plus 0. Can I ever get 3 from sums of this, right? The answer is no, right? Like 1 plus 1 is 2, 0 plus 1 is 1, 1 plus 1 is 1 plus 0 is 1, this is 0, right? So this is impossible if P is 3 mod 4. So you sort of see that there's no such thing that gives me norm P in this case. So this is a contradiction. Does everyone follow? So here's an example. So basically, now you know in the Gaussian integers, all primes congruent 3 mod 4 are actually prime in the Gaussian integers. 1 mod 4 requires a bit more work, but 3 mod 4 is easy. It's just this proof. Everyone follow? Yes? No? Okay. Yeah, that's all I have for today. So I'll see you all Thursday. Yeah. No problem. No problem. Do you all know if he posted the homework? By homework, I mean like because I think he said he's gonna give you additional problems, right? Because there's like what, like 4 book problems or what? But he did say that in lecture, right? Like he was gonna give you problems on Gaussian integers.
He said he would change